Okay, so in this video we're going to be looking at using orbital diagrams in order to answer some questions about the various behaviors of an atom. In this case we're going to talk first about how many unpaired electrons there are in an atom of iron, and then does that make it paramagnetic or diamagnetic. We obviously need to understand those terms first. So paramagnetic, just as a reminder, is referring to a case where an atom shows magnetic properties because its spin states of its electrons are not canceled out. So if you have any unpaired electrons, it's going to have an unbalanced spin, and therefore the magnetic fields will not cancel each other out. It will have magnetic properties. Diamagnetic refers to when all of the electrons in the atom are paired in their orbitals, and therefore with those spins paired we have no magnetic properties. Okay, so in order to do this for iron, the first thing we're going to need is the electron configuration. Okay, you can see the previous video how to do the whole one. I'm just going to write it out in the shorthand. So we have Fe, which is the noble gas shorthand, is going to be argon. That's the last noble gas we've completed. And then we're going to come along and say 4s2, and the iron has 6, so that'll be 4s2. Or we start into the 3D now, so 3d 6. Okay, now looking at this, when we write out the orbital diagrams, there's a couple ways you can do it. You could just do it with a line, kind of like this, and say that's the 4s, and there should be 5, right, because a d orbital has 5 suborbitals, so this could be the 3d. Okay, so that's one way to do it. The other way is to just box it, so you could say that's the 4s, and then you draw a series of boxes for the 3d. Okay, either way it's going to be the same. You would simply label 4s 3d. Okay, I'm going to go with the boxes, just it's a little bit simpler to do at this point. So when I'm going to put these electrons in it, so I know I have 2 in the 4s. Remember, one has to be spinning up, the other pointing down, representing the opposite spin states, and that's just anytime you have 2 orbitals, because of the Pauli exclusion principle, 2 electrons in an orbital, they need to have be the opposite spin. Okay, we can't share identical all 4 quantum numbers. So if we look at the 3D, there's 6. So I'm going to put them in order: 1, 2, 3, 4, 5. Okay, originally we spaced them all out like this. They're electrons. They don't like to be jammed next to each other if they can help it, because they will repel. Hund's rule states that we need to maximize the same spin, and therefore all of these that we put in should be the same spin initially. And then we have one more to put in, a 6, so we'll put it right here, pair it with that one. That's the one that's going to be down. So now we can answer this question: how many unpaired electrons are there in an atom of Fe, and is it paramagnetic or diamagnetic? Well, we have 4 unpaired electrons, and because we have unpaired electrons, this element is therefore paramagnetic. Okay, so that's how we use orbital diagrams to answer questions about the nature of that atom and the electrons and so on and so forth. In the next case, we're going to look at a different one, and we're going to see sort of how you might deal with some exceptions. Okay, so copper, how many unpaired electrons are there in an atom of copper? If we go through and fill this out, okay, the first thing I'm going to do is just write out the electron configuration of copper. Right, so copper is going to be, the last thing that we filled again is argon. And we have 4s2, 3d9. Okay, this would be your sort of initial shot at, you'd say 4s2, 3d9, that brings me to copper. This, however, happens to be one of the exceptions. Okay, copper, along with silver and gold, are exceptions in that it's a little more stable at this point to have a half full shell and a full shell than it is to have 9 of the 10 electrons in the D. So it turns out that what copper actually does is it changes from this to, it's going to have argon, 4s2 will become 4s1, and we'll have 3d 10. Okay, so if we were to look at this from the standpoint of the orbital diagram, right, we have our 4s, and we have our 3d, and originally our thinking was that we would fill it with, okay, up, down, up, down, up, down, down. This would be 4s2, 3d9. Okay, but that's not correct. Because of this right up here where we change it's 4s1, 3d10. The reason, if you look at this, we've got that 9/10 full. Well, this diagram right here, if we did the 4s, we'll remake the 3d down here. Okay, when we put the electrons in this way, here we've got the 4s is now half full, and again I said half full and full shells are more stable. This is now a completely filled d orbital. Right, all the suborbitals here, all 5 varieties of this 3d are filled, and therefore how many unpaired electrons are there in an atom of copper? In this case there's just one. Okay, the answer would be the same for either one when you looked at it, but this is the top one is an incorrect drawing of the orbital diagram. This one is correct. Okay, this is also why it's sort of a common case where you could form a copper +1 ion. Okay, you can also form the +2, and there's another one, but the +1, the first thing you're going to take off is going to be that outermost, and in this case that's the 4, right? So the 4s, that one electron would come off and leave you with copper +1. Okay, when you go to copper +2, you would then need to take out the d as well. Now, one of the other things to think about with this is that do not get sort of half and full shell crazy and start trying to do it with the p's and things like that. That does not actually happen. Alright, so really quickly let's just talk about where these exceptions lie. So if we take a good look here, we can see that we're talking about copper, which is the one we just did, silver, and gold. And all 3 of those, it's going to be a case where they have something S2 and D9 would be our thinking. In the case of copper, 3D9, silver, 4D9, gold, 5D9. And what's going to happen is they're going to essentially take their S down by 1 and make it 3D10, 4D10, 5D10. So the exceptions you're talking about are really those 3 right there. Okay, this does not happen out here in the P's, so don't try to make carbon become, oh, we'll just make it 2s1, 2p, 3. Okay, that doesn't happen. It's just because the s and the d orbitals are so close in energy level that lets it do that. The other 2 we need to know that do this are chromium and molybdenum. And when they do it, if you note, they're at, so chromium is 4s2, right, there's your s's, 3d4. Okay, so what's going to happen is it's going to become 4s1, 3d5. Okay, molybdenum will become 5s1, 3d5. Okay, tungsten it doesn't actually occur with because tungsten has those F's and there's sort of not that much of a difference. There's a bigger difference, I guess, between the D's and the S's. So that actually does not do the borrowing. So it's really these cases right here that I've sort of outlined. Okay, chromium, molybdenum, copper, silver, gold. Just know that if you write those out as S2D9 or S2D4, you should stop and think that probably what you need to do is go back and change that to S1D10 or S1D5.